Thank you, Jonathan, for a nice and kind introduction. This sort of really kind of brings me back those 20 years ago, where I'm thinking about what kind of problems we were working on back then in the context of autonomous driving and vehicles and hybrid systems. And now we are 20 years later. We are in very different times, and so I hope I'll be able to kind of at least inspire you and think about different interesting and exciting problems in the area where perception means control. In the second part of my tutorial, I'm going to focus a little bit more on kind of technologies and methodologies which are currently being applied in this domain. So I'm afraid it's going to be a little bit disappointing when it comes to delivering some deep theory, but at least I'll sort of chart a little bit the landscape, and hopefully I feel like it will at least illuminate the difficulty of some of the problems. And I think this is hopefully kind of a good avenue and platform to start interesting discussions of what kind of problems we have sort of a better chance of tackling and how. So let me just do a quick recap what I have done in my first part of the tutorial. And the first part of the tutorial was somewhat sort of detached from autonomous driving problems. We were mostly focusing on setting up the stage of how to tackle different perception problems. And let me just put my headphones so you can hear me better. I completely forgot about it. Just 1 second. All right. So I basically introduced 3 problems. One problem was this problem of image classification. So this was the problem of given an image and predict the label of the object of the image. And this was really the class of problems where a lot of these deep learning methodologies first got instantiated in terms of having sufficient amount of data, being able to train large models. And I gave you a little bit of a tour of how this evolved, what were the kind of criteria which were driving the architecture selection, what were the methodologies for training. I discussed a little bit sort of this size of the model versus accuracy versus speed trade-off. And this sort of hopefully gave you a little bit of a history and also showed that these techniques are really sort of applicable to a lot of practical settings, dramatically improve the accuracy of the currently performing models. The other kind of takeaway message is that they really sort of enable us to kind of bypass this stage of this human engineering of features and trying to figure out what to extract from the sensory streams. And these representations are basically directly learned through some sort of supervision. And so the 2 other problems I talked about was this problem of object detection, where you have an image and you would like to predict the locations of objects of interest. And this is a setting where you want to predict multiple objects, possibly of different categories, and you would like to associate some confidences with these predictions. And the third class of problems which I talked about are these problems where you would like to do this per pixel predictions, where you take an image and you want to basically solve this labeling problem where per each pixel you're going to make some prediction. And these predictions can vary. They can be predictions of semantic classes of the categories. In that case, you would get this representation of the environment in terms of so-called semantic segmentation, but you can also predict depth. You can sort of predict various quantities. So how is this relevant for autonomous driving? So autonomous driving can clearly be enhanced when we have better perception of the environment. And while a lot of the autonomous driving is currently kind of assuming the availability of very accurate maps where this information is provided, you can imagine that the real world, these maps are not being updated so frequently, and the real world often differs from whatever information about the environment the maps provide. So even being able to online determine exactly what are the drivable areas, where the lane markers are, which is typically the information which is provided by maps, is of interest, because you can imagine roads can be blocked, you can have various obstacles, constructions, what have you. And these are problems where one needs to consider when one strives for this full autonomy. The other problem where the object detection component is of great interest is the ability to detect the other traffic participants. This can be bicyclists, cars, pedestrians. These are the sort of the most commonly encountered. And then you can imagine you can have cars, different variety of cars. You can have trucks and trailers. You can have bicyclists and trailers. So this is all the variety you typically encounter on the roads. And the third component is the semantic segmentation, which again, you can imagine that, you know, being able to figure out where the free space is, where the walkways are, and maybe, you know, even some sort of higher level information, sort of trying to understand whether you are driving in urban area versus in the countryside can also affect the driving patterns. And the hope is that with the help of perception, you can sort of assess these situations automatically. So I want to just do one quick thing I didn't finish last time. And this is sort of a slight addendum to this problem of object detection. So the architectures which I discussed yesterday were sort of this sort of first take on the problem where the predictions for objects were done only at the level of bounding boxes. So you would simply, in addition to estimating the object category, you would provide an estimate for the location of the object, and the location would be specified in terms of bounding box which encloses this object, and the bounding box would be specified in terms of x, y coordinate and the bit width and height. But this, of course, is not a good fit for certain objects because this requires that the objects are kind of nicely aligned with the image grid. So combining some of these insights from semantic segmentation, which generates these pixel level prediction models, there have been some additional advancements made that even for the object detection, you actually can learn how to predict the actual segmentation of the objects within the bounding boxes, and this then sort of enables you to have more accurate predictions. So this type of models, the sort of the best performing models is the so-called mask RCNN, where in addition to the regions, the model also provides the segmentation masks. So I'm going to give you some examples of what the predictions of this model look like. So you can imagine that you can predict the accurate contours of the objects. And here we have some examples from the natural world where we have some elephants, but this also works for pedestrians. Notice that here we again have sort of nice outlines of the cars, and then we can sort of have a better ability to also detect parts of the cars which are occluding and sort of push the performance to more challenging scenarios. So all these developments and architectures which we were discussing previously sort of operate in this supervised setting. So basically there is a data set which the community created. the data set is labeled with different level of granularity. And by granularity, I mean different things require different effort when it comes to labeling. So if you want to train a model which can detect segmentation masks, you need this type of information as a part of your training data. So it requires somebody go and, label the actual contours of the objects within these bounding boxes. And as you can imagine, this can be quite tiring. So there are a lot of efforts in how to kind of ease a little bit the burden of this labeling process by using some semi-automated techniques with humans in the loop. And there is actually an entire industry of companies which offer to do this labeling by developing tools, how to do it accurately and efficiently and at low cost. So this is sort of the supervised setting. So if we would like to apply these techniques for autonomous driving, we need data sets which come from these environments. So one of the first data sets which was acquired and put together for the purposes of deploying these machine learning techniques was this Kitty data set. This is has been put together by Karlsruhe Institute of Technology, and they basically went around with all the sensory suite and traveled the city of Karlsruhe. So you have this little map where they have made different loops, and they have gone and labeled all the cars and in terms of bounding boxes. But in addition to bounding boxes, which were in 2D in images, they actually provided the labels for the actual 3D positions and sizes of all the cars, because you can imagine if all you have is the 2D bounding box, the car can be moving forward, it can be moving sideways. So the actual pose of the car is important if you want to predict the behavior of the car. They also provided ground truth information for depth, which was acquired using the stereo and LiDAR. They provided the ground truth information of the trajectories. And so this was kind of the starting point, how to evaluate some of these models and deploy some of these methodologies in the autonomous driving settings. And this is really kind of this philosophy which has been also commonly applied in another tasks where machine learning plays a dominant role, so such as natural language processing, right? So you need to have some framework of a common task, which in some sense is some benchmark where you can somehow measure the progress. And we can, of course, discuss to what extent these benchmarks are satisfactory and how can we really calibrate these statements where, you have these statements in the news that autonomous cars have kind of driven, thousands of miles without accident, without really being explicit about the types of environments these results have been achieved. So this is, I want to just put it out there.
Jana, I think we maybe have a question here from the audience.
So you have to repeat the questions for me because I cannot see the chat window. So could you do
I think we're going to have the person ask.
Okay, so go ahead. Yeah.
So Jana, unfortunately, I was unable to attend the full presentation yesterday due to another thing, but so this might have been covered yesterday, but I understand completely sort of like 2D versus 3D when this is space. The thing that I'm unclear about is time here. So when you're moving around or things are moving around, right? Time I would expect is quite critical, both in terms of that it adds challenges. Like an object needs to be in each frame to be the same object and not completely reshuffled, but also opportunities. For example, when you move around, you can distinguish a car from a very accurate photograph of a car, for example, and things like that. So could you maybe on a big picture level outline again, what is the role of time in all of these challenges here and what has been appeared and not?
So I am not going to cover the time in detail here. I will touch up on it towards the end of this tutorial. And I have some hidden slides which actually discuss this. But you can think of it from the perception standpoint. There are kind of two different philosophies how you can tackle time. One is that you can think of handling the time aspect just by doing a repeated detection and then some kind of matching over time, where the predictions are made in every frame independently, and then you do some data association, which again, you kind of deploy different set of techniques, which can then tell you that this thing in the frame 1 is the same thing in the frame 2. But the detection is sort of independent. Mm-hmm. The other strategy is the tracking strategy, right? So you basically detect things in one frame, and then you predict where the things would be in another frame, and then you augment that prediction with the current observations. And both of these have been examined and deployed in the context of learning and perception for autonomy. And the idea for, and so there are kind of separate tracking challenges, which I'm not going to discuss here because I'm going to focus mostly on this kind of the single view. I'm going to talk about the time when I'll talk about the control, but you have benchmarks on how well these models can track, for example.
Mm-hmm. But what's interesting is that neither of these approaches would do what one could consider is that when you have a camera that you really do 3D, right? Really 3D by having
No. The things are being tracked in 3D. So I'm going to talk about 2D detection. Today I'm going to move to the 3D detection. So yeah. I'm going to show you.
No. What I mean by 3D is that if you had 3D data, LiDAR, it would be 4D, right? And you do real machine learning on a 4D data.
Yes, possible.
Oh, people do that?
Yeah, people do it.
Okay, good.
So one thing which, so today's part of the tutorial is going to be a little bit of this potpourri of things you can do by basically, so one beauty of this deep learning model is that this model of computation and this ability to do backpropagation on computational graphs, do not think about the backpropagation as sort of the taking partial derivatives of the objective functions. This is how it's typically introduced when you are covering the mathematics of it. But the working of it is that once you define the computational graph, it is the graph itself which determines how the gradients are backpropagated. And this works for arbitrarily complex computations, and the graph itself determines the kind of the structure, how things flow. This is sort of kind of a little bit high level, but I guess I would like you to appreciate the fact that variety of different computations can be done in this setting and then fine-tuned on data via stochastic gradient descent.
Okay.
Kind of that's now big challenge, of course, is what kind of guarantees I can provide. So that question cannot be answered without the data set you are using the training for. Right? And so this is, I think, something which we have to really think seriously about when it comes to deploying these methodologies to systems which require some safety guarantees, for example. So let me, so data sets, autonomous driving data sets, large number of data sets. So I'm not gonna, the table is very small, but you can see that from that first data set, there have been lots of different data sets which people came up with, and they're typically kind of partitioned based on the kind of the size, the diversity. Some data sets are from one city, some data sets are from across continents, they vary in the weather conditions. So they're typically put together to push the challenges of perception. Then they also differ based on what type of ground truth labels they have available. So this then sort of determines which data set is a good fit for evaluating your algorithm. So if you believe you have a new good tracker which achieves better accuracy, then you need to have a data set which has the ground truth tracking, which you can train or not. Or if you, for example, believe that motion computation and flow is good for kind of building predictive models of how the drivers will behave, then you need to have a data set where you want to evaluate the accuracy of computation of these different kind of, we can call them like a visual cues. So here's just kind of a quick rundown of the data set. And I want to mention that there is a really nice overview paper which is called the Computer Vision for Autonomous Vehicles, Problems, Datasets, and the State of the Art by Joel Janai, Fatima Ghani, and company. And they provide a wonderful overview with more than 700 references. So whatever problem you are sort of interested in, they at least sort of can give you a starting point of how people went about it and roughly what's the current state of the art. Okay, so let me kind of talk a little bit how to extend some of these deep learning methodologies to 3D perception. And I'm gonna speed up a little bit just to kind of give you some feeling for the problems, because I see the time is passing. So in the 2D detection, we basically showed how we can train a model that can predict the 2D bounding box. And this was some complicated search, sampling, upsampling, kind of sliding the window, at least conceptually, over the whole image and looking where the hypothesis of the objects reside. But for autonomous driving, it's not enough just to know that you have a car in the bounding box, but you need to also know the orientation of the car, right? So now the question is how to estimate this orientation. So one option is that if you have a 3D model of the car, and if you can associate some 3D geometric key points between the model and what you perceive, then you can just solve a simple regression problem and estimate this rotation, translation, and dimensions of the car. But the difficulty is that it's extremely hard to come up with this data association. So then the question is, can we just learn this data association and this model from the data directly? And so this is sort of one strategy how to tackle this problem. And I'm gonna skip the details of the geometry and the architecture, but the gist of the approach is that if I'm gonna show you lots of examples of cars at the different orientations, and I'm gonna provide you the ground truth orientation of this car, you can simply train a network which will learn how to regress the pose of the vehicle directly from images, as opposed to from some geometric quantities, like a 3D points. And, this is something we can do. And I'm sort of highlighting it as an example of a regression problem, which we are now trying to solve by, in the case of this pose estimation, we'll partition it separately into the orientation estimation and then the distance and the size of the vehicle. And the nice thing about this approach is that the approach is kind of the mix of this continuous and discrete optimization, in the sense that first, we'll treat the orientation as a categorical variable. So we'll discretize it. And we are gonna now generate predictions how likely it is that our orientations is gonna fall into a particular bin. So we are going to first treat it as a categorical problem. And this is good because if you have now multiple extrema, you can imagine that you can actually nicely characterize this distribution, and instead of classical regression, which would find the middle point, you can actually keep the both hypotheses and try to refine both in order to come up with the right estimate. And then the second component is the continuous optimization of refining the estimate within the bin. And so you can train a network with given sufficient amount of training data, and then instead of just, I'm sorry, there is some problem with the font. Instead of just making the predictions of the 2D bounding boxes, you can make predictions of the actual orientation and size of the car as it's sort of moving down the road. And there have been a lot of variations of how to train these models for 3D predictions. So one class of methods, for example, says, well, you know, I know how cars look like. I have a lot of 3D models of the cars. So let me assume that I have some repository of 3D models. And what I'm going to try to do is, while I'm predicting the bounding boxes and the segmentation masks in a parallel kind of tower, I'm going to render my models at different poses, and then I'm going to try to match what I'm predicting with the rendering, right? So this is the kind of model which exploits a lot of prior knowledge about how cars look like, and also has the ability to actually detect cars under high occlusions, because it effectively does this A-model completion, where it's enough when you see just the hood of the car, but it turns out that the rendering of the car at the particular pose is the best fit to what you detect.
Jana, I think we also have a yes. question from Darius.
Darius, go ahead.
Oh, but I also, I'm looking for Darius now. I thought I had it. There we go. Okay. So Darius, please go ahead with your question after you unmute yourself.
Well, okay. The question is just, you know, we know from feature-based methods how sensitive the whole pose estimation is, even to sub-accurate estimation of where things are in the scene. So how accurate can you actually be with the pose estimation if you just do it on a pixel base? And the second question is, depending on how the car is rotated, you get different quality of the pose estimation. So does it have a chance to actually tell you how well it's able to get the pose?
So unfortunately, so I don't have the slide here, but you know, I mean, so this is from our paper, and you can quantify the accuracy of the pose estimates, right? So, and you do it the same way how you do it for any kind of regression problem. So you'll just report the error. So I think, you know, so you have to realize that this model has seen 40,000 examples of cars at different poses, right? So if I were to connect it to these feature-based methods, what the model sort of implicitly learns is what features, which part of the feature map activations are actually informative for that pose estimation. And you can actually go back and look at these activation maps, and they look a little bit like key points, right? Except now there are these kind of softer activation maps, so you are not so brittle when it comes to selecting your perfect key point, which is sort of at the corner of your windshield. So yes, it's sort of, the question is, it depends. I feel this particular type of method, because you are trying to regress directly from pixels, is quite sensitive to the training data, and you need large amounts of training data. But the techniques which actually use some prior models, whether these are renderings of 3D CAD models, or you can also just have wireframe models where you try to fit the wireframe models to the observations and then estimate the pose from the point coordinates of the wireframe model if it's correctly fit. These methods are sort of very promising and typically yield better accuracy and need also smaller number of training examples. Is it helping a little bit? I will be happy to show you give you some intuition for this and the relationship between the key point-based methods during office hours. I'll find the other slides. Okay. So this is when you want to do things from images and using the 3D models. The same object detection methodology can be applied on LiDAR data. So if you imagine you kind of take the plane where the of the LiDAR data, you can apply the same methodology of generating the region proposals, estimating the poses, which we have done in the images, but now the images are basically the LiDAR scans, right? But you input the LiDAR scan, you design your architecture, you have the supervision at the same level, you have the supervision for object prediction, you can train a model. And so appealing part here is that you don't have to brainstorm of what kind of features you need to extract from the LiDAR scans in order for this to be informative for presence of the cars and their orientation. So this is something you can learn automatically. So another, when it comes to 3D and LiDAR, or however you get the 3D information, where it's a class of models which is doing the feature extraction and the processing on voxel grids. So voxel grid is simply a kind of a 3D counterpart of an image, where instead of a pixel, you have a little voxel, which represents some information, occupancy information in the 3D space. So given from some range measurements to voxels, there is some methodology how to simply associate some fixed length vector associated with voxel, and which is some kind of representing the information of how many kind of depth returns did you get from that particular LiDAR measurements. And now once you have a fixed vector per voxel, you are again in the territory that you can train these models, both for detection, categorization, and so forth, because this now fits the deep learning architecture, because you have a fixed input which determines the size of your input of the model, and then you follow with kind of the traditional architectures of these repeated blocks and proposals and heads. So both the LiDAR scans and these voxel grids, before they apply these learning techniques, they first compute some intermediate representation. So they don't do things directly from the raw data. So the first approach creates an image and then applies these image-based techniques. The second approach creates a voxel grid, and then it runs these 3D convolution techniques. So there is another class of technique and methods which are super exciting and interesting, and they lead to a very different type of architectures. This idea of how can you do learning directly with the 3D point clouds. So now imagine that all you do is you have, a big set of 3D coordinates. And because this is a set representation, you need to have models which will generate predictions which are insensitive to arbitrary permutation of these 3D coordinates, because it is just a set. The ordering within the set does not matter. And you also want to be insensitive to any kind of rotation and translation of the coordinates, because this should also not affect classification. So there are these architectures which are not convolutional in nature, because again, the inputs are the point sets, but they sort of attain these representations which have these invariance properties which are desired for the 3D point clouds. And this is sort of the work of, this is the so-called PointNet, which sort of came from Stanford Vision Graphics Laboratory. So I'm just going to overwhelm you for a few seconds with what is really the state of the art, just to at least understand, given the evaluation benchmark, how well can we do and how we are evaluating these things. And again, this is conditioned on the data sets for which we have the ground truth available. So if you just look at the kind of the very top row in each category, and the letters are extremely small, so let me just read it to you. So we have the 3 rows is the ability or the accuracy of detecting cars, pedestrians, and bicyclists. So these are the 3 object categories which are labeled in these data sets. And then the x-axis, let me just get fancier here and use my marker. So this axis is, this axis is indicating whether the examples are easy, moderate, and hard. And what this means is that if you have a car where 1/3 of the car is completely occluded because the car is parked, this is an example of a very hard detection. And the easy detection is when the whole car is visible, and the moderate is in between. So for the cars, I think things look quite okay. There is 89% accuracy of the moderate, 97% accuracy of the oh, sorry, I'm actually here reporting, this is the orientation estimation of the easy, and then the 80% hard. And I want to clarify that the orientation estimation is, the accuracy is reported by, and what is meant by that is that how frequently it falls within a particular bin given certain quantization, right? So here in this evaluation, the orientation estimation is treated as a classification problem as opposed to the regression problem. And then you can, of course, choose different granularity. So you can say, I'm going to have 8 bins, or I'm going to have 12 bins. And so if you sort of dive deeper in some of these results, that's what it tells you.
Another question from Darius. Darius, go ahead.
Yeah.
Well, we talked about this already yesterday. Do you know how large actually this bin is? So what's the deviation?
So I think, so imagine that you have, so we can go back. So here, sorry, let me use this. So you have 360 degrees. So if you have 8 bins, so you can divide it by 8. If you have 12, I have a picture here. So
but this just means that you are within 12 degrees accurate, which is really not a great thing.
But this is just, so here the statement, you can be more accurate than that, but this is because you can still do an additional continuous optimization within the bin, but this is just the choice of the benchmark in order to compare the approaches which treat the regression as a classification on the same footing, right? Yes, so it's within kind of 10 degrees. And, so you can decide this is useful when it comes to driving. It definitely
But but the conventional approaches were within 1 to 2 degrees. Now we are speaking 12 to 15 degrees. So we are going somehow backwards in the whole evolution. We used to be more accurate than we are now.
But this is not, so you can attain, so I just do not have it here, but certain papers, you can actually attain the actual error between the ground truth pose, which is the continuous quantity, and the estimates, the predicted pose. So what I'm trying to say is that we are not trying to forgo the accuracy, although I'm not reporting it here. But this is kind of an assumption to be challenged. To what extent you can use the traditional technique, and how would you then, because if you have a traditional technique, you have the following settings. You either get it right or you completely fail, right? If you use the regression. And now if you're going to run it on thousands of examples, then, how are you going to compare things on the same footing? So what's being suggested here is, well, I'm okay if I were to choose between failing and having something within 12 degree of accuracy, I'll take the 12 degree of accuracy. This is,
maybe we do it office hour. Maybe we do it on office hour, because I think
yes,
it's destroying your talk.
I just want you to think about it. I want you to be more optimistic about it. But I understand your sentiment. I don't want to kind of forgo the accuracy. Okay. So this is the estimation. But now notice that if you now look for pedestrians, situation is much worse. So even with this very inaccurate kind of quantification, you do much worse. And this is really related to the fact that, pedestrians are complicated. They can do lots of things. They can wave hands and so forth. So the model itself has difficulty understanding all the variations in the training data. And here, this is the cyclist, and the cyclist situation is complicated in a similar way than the pedestrian is, because if you have models which are trying to estimate this directly from pixels, you can imagine that if you have a cyclist which is carrying the backpack, and you have never seen that before in the training, that model is going to think that this backpack is definitely going to somehow affect the pose estimates. I mean, I'm just paraphrasing here, but want to kind of highlight the need for this large number of training examples. And this is sort of, for example, this model-based approaches works well for cars, but don't work so well for pedestrians or bicyclists. So this is sort of still interesting and active area of research. Here is a little bit of kind of overview of the accuracy when it comes to instance level segmentation. So this is not the detection, but this is kind of pixel level accuracy. And that's even lower than in the previous setting. So again, let me just skip, because there are a lot of things I would like to discuss. So let me just kind of speed through other things you can compute. And, right now, this is sort of a big open problem when it comes to which of these visual representations are the most informative for driving, or, and for control, because we have the raw sensory measurement, but we can compute a lot of informative things, but we don't quite know what is that state space where we should formulate the control problem. And this is something I'll touch upon a little bit. So here is sort of an ability to compute the depth maps using the stereo. You have an ability to compute the flow. So if you have two consecutive frames, there's a lot of work when it comes to design of different architectures, how to compute the motion between the frames. And this is very important because you can first use it for your own motion estimates for ego motion. So you can figure out whether you are stationary or moving, but you also can understand how the other objects in the scene move. So this can be sort of effective as a starting point for predicting future and sort of trying to understand how the traffic will evolve in the future. So let me just skip these flow models. And again, there are data sets where you can train these models. And a lot of these methodologies basically take the kind of the standard know-how of the techniques which have been developed previously in computer vision community, and they sort of try to implement some deep neural network counterparts, which are then fine-tunable in an end-to-end way. So maybe I want to just spend 1 minute on this kind of the top performing flow model. So here, you are not letting the network to learn the flow from scratch by just passing the network the 2 frames, but you really take the two frames separately. First, you extract some informative features from these models, and then you basically you compute this correlation, but now the correlation is being computed in this high-dimensional embedding space, which you obtain by running these images through convolutional layers, as opposed to convolution being computed in the pixel space, which the correlation. But if you were to compute it in the pixel space, everything would fail. You would be sensitive to a lot of things. But here you basically learn the space over which you should compute the correlation, and then you kind of follow by making the predictions for motion. So I wanted to get back to it just to highlight the fact, to show you different examples of the kinds of computations you can do in these networks and how you can design these architectures to do so. Okay, so more on flow. So the other thing you can do is you can fuse the information from multiple sensing modalities. So here is an example which is using the car detection from multiple views. So first you take the bird eye view of the LiDAR, then you take the front view of the LiDAR, and then you take an image, and then you generate these predictions from all these multiple sources, and then you kind of get the final classifier, right? So this is also, there are sort of a lot of different methodologies for this fusion. Sometimes you just concatenate the feature maps. Sometimes you do some kind of softmax computation in order to sort of pick up the confident high activation models and so forth. So this is a little bit on using both vision, LiDAR, and overhead bird's eye view for the detection. I will skip these. These are some examples of depth recovery. So here are the challenges, right? You're always going to think, you always can see things which you have never seen before. So, again, people are pushing and understanding some of these rare cases, which created the challenges for when it comes to accuracy of these predictions on the things which really matter, right? You don't want to miss a pedestrian, you don't want to miss a bicyclist. So again, there are efforts of designing data sets where you can see that the pedestrians are not your usual walking down the pavement pedestrian, but they are in a really challenging poses, in costumes, carrying various things, running. And, so some of these models have some insights how to handle these rare cases. Another challenge is very difficult lighting conditions. Lighting matters. You want to be able to do it at any time of the day, under any weather and season. So there are data sets which try to push the diversity of the data along the kind of the weather and season direction, because, imagine that you are driving at sunset and the sun is shining directly into your camera. So can you still do it? And some of these aspects are a matter of sensor choice, and or maybe you can have some fusion mechanisms, but to some extent they're also interesting to consider from the intellectual standpoint. Here are some more challenges. A lot of things, you can find a lot of things on the roads which you have never seen in the training sets. Unusual vessels, vehicles, obstructions, and what have you. Okay, so let me spend the remainder of the tutorial discussing some ideas which are out there when it comes to control. Because at the end, the reason why we are trying to understand better the environment and be able to have this kind of most up-to-date snapshot of what's out in the world is to actually guide our decisions. So in some sense, we need to somehow connect the things to the decision-making. Because you can argue, well, I'm running all these object detector benchmarks and I'm trying to push this accuracy for correctly detecting this car, which is 100 meters away. But in reality, it probably doesn't matter whether I get that car correct or not, if all I care about is me doing the lane change, right? So this is now, I'm gonna shift a little bit the gear to thinking about what really matters for control. And in order to do that, we need to even sort of do a couple of these exercises, how we can go about the control and how to sort of integrate it jointly with the perception in the context of these learning frameworks. So this is, let me kind of wrap up the deep neural networks for perception, just by leaving you with these thoughts that, and this actually also extends to the control, is that the main appeal is this ability to optimize a particular problem end to end given the data. And this is sort of one way how you can really test the robustness of these models. And then the rest is, all the magic when it comes to designing the architectures, training the models, using all the training tricks. And this is now where a lot of the know-how is moving to. And some of the know-how is, being replaced by strategies where you learn the architecture. But again, the landscape is really kind of wide and undulated, so you need to sort of pick your battles, I suppose. So again, so what's next is sort of trying to think how to tie these models for control, and what can we really provide that is useful, right? So right now, we focus only on this kind of single snapshot prediction, but imagine that it's important to have some ability to forecast the future. And so this is something a lot of people are looking at, because when you are making a particular decision to do a certain maneuver, that decision is definitely affected by some assumptions what other participants will do in the future. And then the question is, how can you learn to do this? So there are a lot of data sets which recently Lyft released a data set which is suitable for this forecasting, right? So they have a lot of examples of labeled trajectories, these snapshots of trajectories where you have ground truth information about all the traffic participants over a particular snapshot of time. But let's sort of stick a little bit with the learning part. And I want to make sort of a couple disclaimers, because I think a big part of the audience actually has a lot of control background. And so while I'm sort of presenting some of these ideas of how to tie the perception to control, the exercise here is really thinking about how we can use these models, which we can fine-tune and train in setting where some of these engineering decisions are very difficult. Now, if you have a control problem where you are not faced with these difficult decisions, you should sort of, and it's not only difficult decisions, but the current decisions you have are not robust enough. And you believe that if you have large amounts of data, you can make more informed choices. So this is where the learning comes in these settings. So the simplest way how to start thinking about the control component, that, you know, before we had an input was image and we could output a class probabilities, and this is a supervised problem. I can train a network to do that. So you can think of tackling the control problem in the same way. I will give it an image, and now instead of semantic classes of objects, what I'm going to do as an output is I'm going to have the control commands, right? So, and you can imagine that it's probably not that difficult to gather a lot of training data with examples of images and control commands, because you just drive around as in kind of a supervised setting and record a lot of these trajectories. So this was indeed, one of the first approaches to sort of try to apply these deep learning techniques to driving by NVIDIA. And the idea was, well, how can you learn end-to-end driving? So, instead of going and detecting the lane first, let's just learn how to drive directly from images. We'll skip this intermediate representation state. Because you can argue that if I know where the lane marker is, I can design a very nice stabilizing controller with delays, which will just keep the fixed distance from the lane marker. But, lane markers, sometimes they get occluded. Sometimes the lane marker detection fails. So these are some of the choices one has to make. So yes, we can do that. So the problem with this, so this is sort of a way how to think about the control in the supervised setting, where you have a lot of examples. And so the problem with this supervised setting is, and sort of the algorithm of choice which you have, this is the so-called dagger. So you have some sample trajectories, you will train your model, but the problem here is that it's very likely that if you go to the new environment, the examples or the observations which you will have are going to be the observations which you have never seen before, and this is going to effectively cause the drift of your control strategy, right? So this is the idea of you are expecting, this is the training trajectory, and then you learn the policy on this trajectory, but now you have a different observation, so this is going to be the policy, this is going to be the trajectory under the new policy, and you will gradually drift away. So there are a lot of techniques how to kind of handle that, but in essence, they all require just gathering the more training data. And this is sort of the idea behind the dagger, that you simply, you first train the policy, then you run the policy, and then you ask the humans to label all the data. And then you take that labeled data and create this new aggregate data set. So I forgot to also mention one sort of nice thing, how this NVIDIA strategy took care of this was the following, that in order to avoid this problem or make it a little bit less severe, this problem of encountering an unknown data, during the training stage, they had these side cameras, which basically had the views as if you would be slightly veering off from the main road. And these were the views which were labeled with these corrective actions. So if I'm slightly veering to the left, then correct to the right, and so forth. So although they have never, they never had to drive in this wiggly way, they had this mechanism how to acquire the data which corresponded to some of the deviations from the normal driving. So this was kind of a neat idea. But still, applicable only to the limited setting of pretty much driving on the curved roads. This is not something which can kind of handle stops and intersections and complicated maneuvers. One small little addendum that for a lot of these control problems, you want to have a little bit of history, and there is a module which you can train in order to kind of learn how the representations from the previous state are related to the representations in the consecutive state. So you can think of it as learning some dynamics in the embedding space, where the embedding space is the representation extracted by the neural network. And this is typically done using these recurrent neural network modules. So this is now, the prediction is, instead of being made from a single frame, it's being made from the sequence of frames. So let's talk briefly about a couple ideas how to kind of extend it to a little bit more realistic and challenging driving scenarios. So first idea is this idea of so-called goal-conditioned behavior cloning. And this basically assumes that you have some kind of set of these strategies which can be, keep on going straight, turn, or stop at the intersection. And these are qualitatively very different controllers are needed in order to kind of be in each of these modes. But if you can sort of, if you can partition these, you can have the training of the final policies be actually conditioned on the command. And the command here is basically, you can think of it as another hierarchical controller, which is telling you when you should turn, when you should keep on going straight, and when you should stop at intersections. So this is something which is given to you by kind of another higher level controller. And so what the policy then learns, conditioned on this higher level command and some measurements, where the measurements are, say, vehicle velocities, it's still going to learn how to avoid all the obstacles, moving cars, not bump into things, not go on the pavements, but while sort of following the higher level commands. And, here, this type of problems are typically tackled in simulation. And so there has been a lot of efforts in this sort of learning for control field to develop high fidelity simulators where you can train these models. And then there is a separate subfield which is sort of worrying about how to do the simulation to real transfer. But just to sort of give you some feeling that, so this was, the accuracy of these strategies is about 89% in the simulated environment. But note here that these strategies don't do any car detection, they don't do any road detection, they don't do any landmark detection. So they basically completely skip that intermediate state and try to learn the policies directly from the data, from the observations. I have a couple more examples of these variations, how to go about learning in these settings, but I will just kind of fly through them. These are simply different variations, how to provide the different supervision, either using this kind of fully supervised setting. There are approaches which use kind of the more core reinforcement learning techniques where the supervision only comes in terms of rewards as opposed to exact supervision at every step, which you have in kind of this so-called imitation learning, which is the version of the fully supervised learning for control. So let me just skip through these. Here are sort of some differences trying to highlight between the supervised learning, which we have discussed so far, and the reinforcement learning. And sorry. And so the essence of these strategies is that, again, they're typically trained in the environment, and then in the reinforcement learning, the challenge is really how to define the right reward systems in order to train the agent. Let me skip this because we are nearing the end. So you know, some of these examples which I highlighted so far were sort of taking this idea, well, I don't want to really compute these intermediate representations. I want to learn directly from pixels, right? And this is very challenging because in some sense, the model for control has to, on the side, learn all the things which we know are already good and which we know how to extract. I mean, and it's not that it has to learn on the side, but you know, somewhere in that network, that information is presumably encoded. So these end-to-end strategies, which have been initially designed, turned out to have a very poor generalization capability, right? So you can, if you're very close to the training scenario, this works well, but as soon as you move out that zone, the performance drops significantly. So this brings this question, well, what representation should we use? Are all the object detections and semantic segmentations and depth recovery, is all of this useful? And so this question for control, and this question was sort of asked in this paper by Brady Zhou, Phil Krakenbull, and Vladlen Koltun, which they asked, does computer vision matter for control? And, you know, truth to be told, it's, I would sort of slightly reformulate the question, which is stated in the title of the paper. But what they were really asking is, can we learn useful policies from these intermediate representations without explicitly constructing the 3D model of the world, right? So basically the difficulty is simply moved somewhere else. And they have shown that if they train these policies for urban driving or off-road driving in a reinforcement learning setting, and instead of putting as an observation just the raw pixel measurements, they will put the semantic segmentation, depth estimation, or maybe the object detection. This significantly improves the performance of these strategies, the control strategies, and this is not a surprise. So one problem with all these approaches to control is that they suffered from a lot of the difficulties these deep neural models have is that they were not really interpretable, right? Because, you know, the network will learn some intermediate representation, but it's really hard to introspect what is really the space where the control is happening. So, you know, there are sort of a lot of explorations which continue in this space, again, in this mode of doing kind of control benchmarks in simulated environments and thinking about how to incorporate more explicit representations of 3D environment and how to combine it with traditional control strategies. So you don't have to go and learn literally the individual control actions, but you can think that you already have some control primitives, which are, for example, obtained by optimal control, and then you have some ability to follow the trajectories, but you don't quite know which trajectory to follow, because this really depends on your better understanding of the environment. So I want to leave you with this last example of a model which really sort of tries to unify more kind of the traditional control with the more modern perception, where you can sort of get these high quality predictions about traffic participants. But what the model learns is, you know, what are the best trajectories to take by sampling the trajectories and learning the cost of the trajectories, where the cost volume, which is now both the space and the time where these trajectories live, what contributes to the cost volume are now both the observations from the perception and also the sampled trajectories. So here is an example which sort of takes the overhead LiDAR map. It does some trajectory sampling, so it generates some trajectories, and then the top branch, I'm having some problems with the pen. The top branch is gonna generate a lot of predictions of where the objects are in 3D space. So it does the 3D object detection. But instead of committing to the detections, it's gonna basically put these predictions into some cost volume, where the cost is going to correctly reflect the confidence in the prediction. So this will sort of take care of the fact that I don't want to really care that much that my prediction of the car, which is 100 meters away, is actually should not really affect that much my current maneuver. And then you will take this, you will basically incorporate these sampled trajectories in the cost volume, and then select the trajectory which has the lowest cost. And I mean, the appeal here is that the cost here is learned. So you have simply a lot of examples of these trajectories along with the real perception data. So you can sort of correctly assess what is the goodness of each position along that trajectory for particular horizon. And these are sort of horizons of short maneuvers, such as like lane changes and moving traffic and so forth. So this is where I would like to leave this. And I would like to open it for discussion, or maybe we can follow up with the discussion later in the afternoon. But this last model is, I think, is a particularly appealing example where you have an opportunity to marry the sort of the traditional control and kind of the trajectory generation and the following with the real world perception. And the control is helping the perception not to care about things which are irrelevant to the control problem. And you can choose the right kind of trajectory by considering the real kind of online perceptual data which come in and the predictions from real sensors and kind of the real-time moving traffic.
Excellent. Well, thanks so much, Jana.
You're welcome.
For the talk.